Introducing the railroad-powered cogeneration system. As you are no doubt well aware by now, global warming is having a significant impact on our nation's economy and living conditions. Reducing sources of carbon input into the atmosphere has become a serious matter, and scientists the world over are working on ways to solve the problem. Two areas that pour significant amounts of carbon into the atmosphere are the production of electricity via the burning of fossil fuels and transportation methods utilizing gas and diesel-powered vehicles. We believe that our railroad-powered cogeneration system, or RPCS, can be of significant benefit in both these areas. What is RPCS, you might ask? RPCS is a novel method of utilizing the efficiency of railroads to produce compressed air at a very low cost. Even though compressed air is recognized as a clean, readily available, and simple-to-use energy source, it has also been labeled by the Department of Energy as one of the most expensive forms of energy on the planet. From DOE's comments, it would seem that previous methodologies for creating compressed air were judged to be extremely costly and inefficient, so compressed air was ruled out as an energy source for generating electricity. However, we at RPCS believe that our invention can greatly expand the role compressed air can play in producing electricity, while at the same time it enhances the utilization and profitability of one of our most efficient forms of transportation, railroads. By doing this, we hope to one day eliminate the need to burn fossil fuel at power plants in order to create electricity, while at the same time we help reduce the number of diesel-burning trucks on our nation's highways. Here is a simplified version of how energy can be tapped cost-effectively from moving trains. First, diesel fuel is burned by a locomotive in order to bring the train up to speed. The fuel to do this has been paid for by the customers of the train company who need supplies or products moved from point A to point B. Once the train has been brought up to speed, the kinetic energy of hundreds of tons of moving mass becomes focused on the wheels underneath each train car. Our RPCS equipment, which is attached to the rails, interacts with the train wheels to force a pocket of highly compressed air along a special hose until it's shunted away from the rails and into pipes buried under the tracks. From there, the compressed air is routed to a nearby storage area that is capable of handling large volumes of compressed air, such as an unused well, abandoned mine, or a special bladder at the bottom of a lake. Once the compressed air is in storage, it can either go to a local power station that utilizes compressed air-driven power generators to create electricity, or it can be directly piped to the types of industries that use tools powered by compressed air. From the power stations, electrical energy can be relayed to either the national ISO grid, the regional ISO grid, or local municipal utility districts for distribution to all who rely on electricity. Earlier in the presentation, it was stated that RPCS can create compressed air in a very cost-effective manner. So before we look at the actual working of the system, let's address that issue first. In the last slide, we stated that the cost of getting railroad trains up to speed was borne by the customers of the railroad service. Trains do need to slow down from time to time when going around curves and when coming down from the mountains, and they need to stop when they get to their destination or when they have to pull over and let another train pass. When they do any of these things, they waste some or all of the kinetic energy that they work so hard to create. Our system could be implemented anywhere that trains need to stop or slow down, and we would basically be recapturing that energy for them, much the same way that the braking system in a Toyota Prius is able to capture some of the energy that would normally be lost when the brakes are applied. However, our calculations have shown that our system can also be used in trains traveling at cruising speeds without impacting their fuel usage by more than 10%. Since they are already getting very high rates of ton miles per gallon of fuel, somewhere in the neighborhood of 470 ton miles per gallon, it means that our equipment can create large volumes of compressed air at extremely cheap rates. There are two main reasons why creating large amounts of cheap air pressure is important. First, it can be used in pneumatically powered electrical generators to create electricity without adding any additional greenhouse gases to the environment. The only fuel needed is compressed air, and the only exhaust gases are clean air. And second, it can be stored. Being able to store the compressed air gives us an advantage over solar, wind, and hydropower. When the need is low, we can store the compressed gas until such time as it is needed. Wind and solar have trouble with that. If they are producing electricity during a time when the need is low, the electricity is lost. By having the ability to store compressed air, we then have the ability to make electricity even if the sun isn't shining, the wind isn't blowing, or the dam is empty. Now let's look more closely at the equipment that will be attached to the rails and generating the compressed air. This drawing is a cross-section of a single rail and the attachments that the RCPS will make to it. On the right, you see the familiar I shape of a steel railroad rail. On the left side at the bottom, you can see what looks like a truncated right triangle with a hole in it. That is a support structure that will be attached to the rail. Its job is to provide the platform for the gear that does the actual work. Just above the support structure is what looks like a blue oval. That is our air compression hose. Just above the air compression hose is what looks like a gray-colored box with a bite taken out of the top. That is a rubber tread cap that acts as the interface between the actual train wheel and our air compression hose. And in dark gray, above the rubber tread cap, is the part of the train wheel called the flange that sticks over the rail and does the job of holding the train car onto the track. In this instance, the flange is doing double duty. It's keeping the train on the track, and it is also pushing down on our rubber tread cap and helping us compress air. Now there are only 4 moving parts to each air compression hose unit. At the heart of our system, seen as the dark blue oval with a teal-colored interior, is a cross-section of longshoreman's hose of the kind used in port facilities around the world. This type of hose is noted for its hardiness and its ability to withstand pressures up to 3,000 pounds per square inch. Each of our air compression hose units will be based around a 12-foot-long length of this hose. Here's another look at the hose, along with some of the specs. The inside and outside of this hose will be reinforced with steel leaf springs. These will help protect the hose and provide the recoil action to suck in more air once the train wheel has passed overhead. Our third moving part is a set of steel hinges similar to piano hinges that bind the inner and outer leaf springs to the hose. They are shown in dark brown and can be seen on both ends of the oval hose. Our last moving part, the rubber tread cap, is bonded to the top of the hose spring apparatus. It is a series of rubber segments 3 inches tall by 1.5 inches wide that will serve to transfer the force from the train wheels to the air compression hose unit, as well as to help soften the vibration and noise generated from the interacting components. In this slide, we are looking down from above at a section of the track. The vertical bands are the railroad ties to which the rails are attached. In this drawing, we are seeing just one of the rails, shown as an unbroken horizontal line. The 2 shorter horizontal lines represent 2 12-foot-long air compression hose units, which are attached to the inside of each rail. Note that there is a gap between the 2 air compression hose units. The length of that gap and the length of the air compression hose unit has been calculated to allow for just the right amount of time for the hose units to be able to refill with new air before the next train wheel begins the air compression process again. Here we are looking at a cutaway view of a section of track and its underlying structure. We see the gap between the air compression hose units, and we can also see how the end of each hose leads to a pipe that travels underground to carry the compressed air away from the track and toward the storage area. Along the way, the air will travel past check valves that operate similar to the way valves in human blood vessels operate, ensuring that the air is always flowing in the correct direction, no matter which way the trains may be passing overhead. Let's zoom in now and have a look at our RPCS equipment in operation. At the very top of the slide is an arc that represents the train wheel flange as it rolls along the inside of the track. The flange is pushing down on our rubber tread caps, marked in yellow, and they in turn are pushing down on the air compression hose unit, forcing the air inside, colored in red, to move ahead and out of the end of the hose. On the opposite end, after the train wheel flanges pass by, the leaf springs recoil, opening up the hose, and the fresh air, colored in blue, is drawn in to refill the hose. In the drawing, you can see that we have added air filters and dehumidifiers to process the air as it enters the hose. Here we see pretty much the same thing we saw in the last slide, only from a different vantage point. If a worm living directly under the railroad tracks had X-ray vision and could look straight down the tracks, this is what he would see. Finally, we have a bird's eye view looking down at the gap area between the air compression hoses on both rails. The major benefit offered by the RPCS is its ability to replace costly traditional methods of compressing air. This compressed air can be utilized to produce electricity in large enough quantities to power cities without burning any additional carbon-based fuel other than the small amount needed by our railroad trains to create the compressed air. Just as important is the fact that compressed air has the potential to solve one of the major problems faced by all other systems for producing electricity: storage. Once you create electricity, it has to be used immediately or it goes to waste. Battery storage systems are extremely expensive and a potential environmental threat. Compressed air can be stored in underground and underwater storage areas until it is needed. Next month, we will look at the many ways that creating electricity using the RPCS method can help make our world healthier and safer. Thanks for your time and attention.